Welcome to another gentle journey through the mysteries of our universe. I'm here with you tonight, wherever you are, ready to explore something that challenges everything we think we know about distance, connection, and the very fabric of reality itself. Imagine for a moment that you could observe effects that appear correlated on the other side of the galaxy without any signal passing between them, without any delay, without any physical connection whatsoever. It sounds impossible, doesn't it? Like something from the realm of magic rather than science. And yet, this phenomenon not only exists but forms the foundation of our most advanced quantum technologies. It's called quantum entanglement, and it represents one of the most profound mysteries in all of physics. Tonight, we're going to drift slowly through this quantum landscape together, exploring how two particles can become so deeply connected that measuring one is found to be correlated with the state of the other, no matter how vast the distance between them. We'll discover why Einstein himself was so troubled by this phenomenon that he spent decades trying to prove it couldn't be real. And we'll see how modern experiments have not only confirmed entanglement, but revealed it operating everywhere, from the heart of protons to the collisions at CERN's particle accelerator. This isn't just abstract physics. As we'll explore, quantum entanglement is already reshaping technology, enabling theoretically secure communication systems and quantum computers that could solve problems beyond the reach of any classical machine. But perhaps more intriguingly, it's forcing us to reconsider our most basic assumptions about the nature of reality itself. So settle in comfortably. There's no need to grasp every detail or remember complex formulas. Just let these ideas wash over you like gentle waves, each one carrying us deeper into a world where the impossible becomes inevitable, where distance appears to lose its classical meaning, and where the universe reveals itself to be far stranger and more interconnected than our everyday experience suggests. Before we dive into the quantum realm, let's establish our foundation by understanding what we mean when we talk about particles and their states. In our everyday world, objects have definite properties. A coin is either heads or tails. A light switch is either on or off. A door is either open or closed. This seems so obvious that we rarely question it, but in the quantum world, this simple assumption breaks down completely. Quantum particles exist in what physicists call superposition, a state where they can be in multiple conditions simultaneously until the moment they're observed or measured. It's not that we simply don't know which state the particle is in, as if it were hiding its true nature from us. Rather, the particle is described by a combination of possible states, like a cosmic coin that spins forever in the air, neither heads nor tails, but somehow both. This concept troubles our classical intuitions because nothing in our macroscopic world behaves this way. You've never seen a chair that was simultaneously broken and intact, or encountered a person who was both asleep and awake at the same time. Yet at the quantum scale, superposition is not an exception but the rule. Electrons orbit atomic nuclei in probability clouds rather than defined paths. Photons of light can travel through multiple routes simultaneously. The very building blocks of our reality refuse to commit to definite states until forced to do so by observation. Understanding superposition is crucial because it sets the stage for entanglement. When particles are created together or interact in certain ways, they can become linked in their superposition states. Their individual properties cannot be fully described independently, but their relationship to each other becomes perfectly correlated. It's as if the universe has decided that while individual particles can remain mysterious, their connections to each other must follow precise, unbreakable rules. Now take a moment to consider the implications of this. In your daily life, you're surrounded by quantum particles in superposition, yet somehow the classical world emerges from this quantum foundation. The atoms in your body, the light reaching your eyes, the air you breathe, all of it built from components that exist in multiple states simultaneously until observed. It's a reminder that reality is layered, with the familiar classical surface resting upon a quantum foundation that operates by entirely different rules. The story of how we discovered quantum entanglement begins not with a celebration, but with a profound disagreement between the greatest minds in physics. In 1935, Albert Einstein found himself deeply troubled by the implications of quantum mechanics, the revolutionary theory that was reshaping our understanding of the atomic world. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper that would become known as the EPR paradox after their initials. They weren't trying to prove quantum mechanics wrong exactly, but rather to demonstrate that it must be incomplete. Their reasoning was elegant and seemingly unassailable. If quantum mechanics were correct, then measuring one particle could be immediately correlated with the outcome of a measurement on another particle, regardless of the distance separating them. This prospect horrified Einstein, not because he couldn't accept strange phenomena, but because it violated what he considered a fundamental principle of physics called locality. Locality simply means that objects are only directly influenced by their immediate surroundings. For something to affect a distant object, it must send some kind of signal or influence that travels through space, and nothing can travel faster than light. This principle forms the backbone of Einstein's theory of relativity and much of modern physics. Yet here was quantum mechanics suggesting that particles could be connected in ways that transcended space and time. Einstein famously derided this as spooky action at a distance, and he refused to believe that nature could operate in such a seemingly magical way. Surely, he argued, there must be hidden variables, unknown properties that particles carried with them, that could account for these mysterious correlations without requiring instantaneous influences across vast distances. Picture Einstein's frustration. He had spent years developing theories that unified space and time, that showed how gravity warped the fabric of reality itself, that revealed the deep mathematical harmony underlying the cosmos. And now quantum mechanics seem to suggest that particles could ignore these careful structures entirely, exhibiting correlations across the universe that defied classical explanation. For decades, Einstein's objection seemed reasonable. After all, how could you possibly test whether particles were truly connected across space, or whether they simply carried hidden information with them? The technology to perform such experiments didn't exist, and many physicists assumed that Einstein would eventually be proven right. The idea that particles could be genuinely entangled seemed too bizarre to be true. But Einstein's discomfort with quantum entanglement reveals something profound about the nature of scientific progress. Sometimes our deepest intuitions about how the world should work are simply wrong. The universe is under no obligation to conform to human expectations or classical logic. As we'll see, experiments would eventually vindicate the quantum view, but they would also reveal a reality far stranger and more interconnected than even the early quantum pioneers had imagined. In 1964, a physicist named John Stuart Bell changed everything. Working at CERN, the European Particle Physics Laboratory, Bell wasn't trying to settle the Einstein quantum mechanics debate directly. Instead, he was exploring a fundamental question. Could any theory based on local realism reproduce the predictions of quantum mechanics? Local realism combines two seemingly reasonable assumptions. First, locality, which we've already discussed, the idea that objects can only be influenced by their immediate surroundings. Second, realism, the assumption that particles have definite properties whether we observe them or not. These assumptions feel so natural that questioning them seems almost absurd. After all, doesn't a tree falling in an empty forest still make a sound? Doesn't the moon exist when nobody is looking at it? Bell's genius was to translate these philosophical questions into mathematics. He derived what became known as Bell's theorem, which demonstrated that any theory based on local realism must satisfy certain statistical constraints called Bell inequalities. These inequalities set limits on how strongly correlated the measurements of two separated particles can be, assuming they are only connected by information they carried from their initial interaction. The mathematics was elegant, but the implications were revolutionary. If experiments could violate Bell's inequalities, it would prove that either locality or realism, or both, must be false. The universe would have to abandon either the idea that influences are limited by the speed of light, or the notion that particles have definite properties independent of observation. Bell's theorem provided a roadmap for testing the foundations of reality itself. For the first time, the Einstein quantum mechanics debate could be settled not through philosophical argument, but through direct experiment. The question was whether anyone could perform such experiments with sufficient precision to reach a definitive conclusion. What Bell had accomplished was remarkable. He'd taken abstract philosophical questions about the nature of reality and transformed them into testable scientific hypotheses. The universe would have to reveal whether it operated according to our classical intuitions or according to the strange predictions of quantum mechanics. There could be no middle ground, no compromise position that satisfied both views. As you contemplate this moment in scientific history, consider the courage it took to question such fundamental assumptions. Bell wasn't just challenging a particular theory or experimental result. He was asking whether our most basic beliefs about locality and realism could be trusted. He was opening the door to a universe that might operate according to principles that seem impossible from our everyday perspective. The experimental verification of Bell's theorem required extraordinary precision and ingenuity. You can't just entangle two particles and measure them casually. The experiments demand exquisite control over quantum systems, the ability to measure particles under conditions where no classical signal could link the outcomes, and sophisticated statistical analysis to detect subtle correlations. The first serious attempts began in the 1970s with John Clauser and Stuart Friedman at the University of California, Berkeley. They used pairs of entangled photons, particles of light that had been created in a way that linked their polarization properties. When they measured the polarization of these photons at different angles and analyzed the correlations, they found something extraordinary. The results violated Bell's inequalities. This was the first direct experimental evidence that local realism was false. The universe didn't operate according to classical intuitions. Instead, it seemed to follow the predictions of quantum mechanics, with particles exhibiting correlations stronger than any local realistic theory could explain. But these early experiments had limitations. The photon detectors weren't perfectly efficient, creating what physicists call the detection loophole. Maybe the particles that weren't detected would have given different results, potentially restoring classical correlations. There was also the possibility that the measurement apparatus on one side could somehow communicate with the apparatus on the other side, influencing the results in ways that mimicked quantum correlations. The next breakthrough came in the 1980s with Alain Aspect and his team in France. They addressed the communication loophole by using fast-switching devices that could change the measurement settings while the photons were already in flight. This ensured that the choice of what to measure couldn't influence the distant measurement, closing off one potential escape route for local realism. Aspect's results were even more convincing. The violations of Bell's inequalities were clear and statistically significant. The correlations between entangled particles were precisely what quantum mechanics predicted and stronger than any classical theory could account for. The universe was revealing itself to be fundamentally non-local, with particles connected in ways that cannot be described by classical local mechanisms. Over the following decades, experimenters closed additional loopholes and pushed the precision of these tests to extraordinary levels. They used different types of particles, increased the distances between measurements, and employed ever more sophisticated techniques to ensure that the results couldn't be explained by classical means. The culmination of this experimental program came with the 2022 Nobel Prize in Physics, awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments with entangled photons. The Nobel Committee recognized not just their technical achievements, but the profound impact of their work on our understanding of reality itself. These experiments did more than confirm quantum mechanics. They opened the door to entirely new technologies based on quantum entanglement. Quantum cryptography, which uses entangled particles to create provably secure communication protocols, became possible. Quantum computing, which harnesses entanglements to perform calculations beyond the reach of classical computers, moved from theoretical speculation to practical development. But perhaps most importantly, these experiments forced us to abandon our classical pictures of reality. The universe is not made of separate, independent objects that influence each other only through local interactions. Instead, it's a deeply interconnected web where distant events can be correlated in ways that seem impossible but are nevertheless real. As we continue our journey through the quantum landscape, remember that these experimental results aren't just abstract physics. They represent a fundamental shift in how we understand the nature of existence itself. The particles that make up your body, the light that illuminates your world, the very fabric of space and time, all of it operates according to these strange quantum rules that connect everything to everything else in ways we're only beginning to understand. The implications of these discoveries ripple far beyond the laboratory walls where they were first confirmed. When you pause to consider what Bell's experiments actually proved, the scope becomes breathtaking. We're not simply talking about exotic particles behaving strangely in carefully controlled conditions. We're confronting evidence that the entire universe operates according to principles that defy our most basic assumptions about how separate things can influence each other. Think about this for a moment. Right now, as you listen to these words, quantum phenomena governed by entanglement principles are actively studied and experimentally demonstrated in controlled systems around us. In the atoms of your body, in the light streaming through your window, in the very air you breathe. In principle, particles that interacted billions of years ago in the heart of ancient stars may still retain correlations encoded within the broader quantum description of the universe, their histories intertwined across the vast expanses of space and time. This is not mystical speculation, but a carefully studied implication of quantum theory. though its direct observability depends on experimental context. But how does entanglement actually work? What does it mean for particles to be connected in this mysterious way? To understand this, we need to venture deeper into the quantum realm, where our classical intuitions must be set aside entirely. When two particles become entangled, something remarkable happens to their individual identities. They can no longer be fully described independently. This doesn't mean they merge into a single particle or occupy the same location. Rather, their quantum properties become fundamentally linked in a way that transcends ordinary space and time. The particles enter what's known as a joint quantum superposition, where their combined state is perfectly defined even though their individual states remain completely uncertain. Imagine two coins that have become quantumly entangled. In our classical world, each coin would be either heads or tails, and you could, in principle, know both states simultaneously. But entangled quantum coins exist in a combined state, where you know with absolute certainty that they will always show opposite faces when observed. Yet neither coin has a definite orientation until the moment you look. The instant you observe one coin and find it showing heads, its partner is found to be tails, regardless of whether it's in the same room or on the opposite side of the galaxy. This correlation isn't the result of the coins communicating with each other or sharing some hidden signal. It's far more profound than that. The entangled system doesn't allow for independent states. The particles have become parts of a single, shared quantum description that happens to be distributed across space. When you measure one part of this system, you're not just learning about that local particle, you're defining a property of the entire entangled system as described by quantum theory, which is reflected consistently across all its components. The mathematics underlying this phenomenon is both elegant and unsettling. The quantum wave function that describes an entangled pair cannot be separated into independent descriptions of the individual particles. It's mathematically impossible to write down the state of one particle without referencing its partner. This inseparability is built into the fundamental structure of quantum mechanics, suggesting that the universe itself operates as a deeply interconnected whole, rather than a collection of separate, independent parts. What makes this even more extraordinary is that distance plays no role in maintaining these connections. Entangled particles have been separated by hundreds of kilometers, with their correlations remaining as strong as if they were side by side. The universe seems to contain what Einstein reluctantly called spooky action at a distance, a phrase he used to describe correlations that defied classical explanation, connections that operate outside our normal understanding of space and causality. As you contemplate this reality, consider how it challenges the notion of separation that dominates our everyday experience. We tend to think of ourselves as isolated entities, distinct from our environment and from each other. Yet if the fundamental building blocks of reality are connected in this profound way, what does that suggest about the nature of existence itself? Some philosophical interpretations suggest that entanglement reveals a universe that is fundamentally unified, where the appearance of separation is an illusion created by our limited perspective. Recent discoveries have pushed our understanding of quantum entanglement into realms that would have seemed impossible just decades ago. Scientists working at CERN's Large Hadron Collider have observed entanglement operating at the highest energies ever achieved in human experiments. In the violent collisions that recreate conditions from the first moments after the Big Bang, particles called top quarks, the heaviest known fundamental particles, become entangled even as they decay into other particles in less than a trillionth of a second. These observations at CERN represent more than just a technical achievement. They demonstrate that entanglement operates across the entire spectrum of physical reality, from the gentlest laboratory conditions to the most extreme environments in the universe. When particles collide at energies millions of times greater than anything found naturally on Earth, they still exhibit the same mysterious quantum correlations that puzzled Einstein nearly a century ago. But perhaps even more remarkable is the discovery that entanglement exists within the protons that make up the nuclei of every atom in your body. Using sophisticated mathematical techniques, physicists have shown that the quarks and gluons inside each proton exist in entangled states, their properties correlated across distances smaller than a quadrillionth of a meter. This means that quantum entanglement operates not just between separate particles, but within the very building blocks of ordinary matter. The implications are staggering. Every breath you take involves countless protons, each containing entangled quarks, whose states are mysteriously connected within well-defined quantum systems. Every chemical reaction, every biological process, every thought and sensation emerges from matter that is fundamentally entangled at the level of its quantum description. The classical picture of atoms as tiny solar systems with well-defined particles orbiting in predictable paths has given way to a quantum reality where the components of matter exist in states of profound interconnection. Scientists have even begun to investigate the temporal aspects of entanglement, discovering that these quantum correlations can emerge on timescales measured in attoseconds, billionths of seconds. Using advanced computational techniques, researchers can now model how entanglement forms when electrons are stripped from atoms by intense laser pulses. They found that the moment an electron leaves an atom, its departure time becomes entangled with the state of the electron that remains behind. In a very real sense, the departing electron cannot be assigned a single classical departure time, existing in a quantum superposition of departure times that only resolves when the system is observed. These discoveries reveal entanglement as one of the fastest processes in nature, establishing quantum correlations on timescales approaching current experimental limits, even as particles separate at tremendous speeds. The universe, it seems, is constantly weaving and reweaving the quantum connections that bind its components together, creating a dynamic web of correlations that spans from the smallest scales to the largest within the framework of quantum physics. As you absorb these ideas, take a moment to marvel at the extraordinary universe you inhabit, the matter that forms your body, the light that illuminates your world, the very space through which you move, all of it permeated by quantum entanglements at foundational physical levels, connecting systems in ways we're only beginning to understand. You are not a separate entity moving through an independent environment. You are part of a quantum tapestry described by modern physics, whose threads extend throughout the cosmos. The practical applications of quantum entanglement are already beginning to transform technology in ways that would have seemed like magic just a few decades ago. Scientists and engineers have learned to harness these mysterious quantum correlations to create communication systems that are theoretically secure, computers that can solve certain problems exponentially faster than any classical machine, and sensors that can detect changes too subtle for any conventional instrument. Quantum cryptography represents perhaps the most immediately practical application of entanglement. By encoding information in the quantum states of entangled particles, researchers have created communication protocols that are fundamentally unbreakable in principle. Any attempt to intercept or eavesdrop on the transmission necessarily disturbs the quantum correlations, immediately alerting the legitimate users to the security breach. Banks, governments, and technology companies are already beginning to deploy these quantum communication networks, creating channels of information exchange that are secured not by complex mathematics but by the fundamental laws of physics themselves. The field of quantum computing offers even more dramatic possibilities. Classical computers process information using bits that are definitively either 0 or 1. Quantum computers use quantum bits, or qubits, that can exist in superpositions of both states simultaneously. When multiple qubits become entangled, they create computational spaces that grow exponentially with each additional qubit. A classical computer with 300 bits can represent exactly 1 of 2 to the 300th power possible states at any given time. A quantum computer with 300 entangled qubits can, within certain algorithms, explore vast numbers of those states simultaneously. This quantum advantage isn't universal. For many everyday computing tasks, classical computers remain more practical and efficient. But for certain specialized problems, particularly those involving optimization, cryptography, or the simulation of quantum systems themselves, quantum computers promise to deliver solutions that would take classical machines longer than the age of the universe to complete in theory. Pharmaceutical companies are exploring quantum computers for drug discovery. Materials scientists are using them to design new compounds with precisely tailored properties, and cryptographers are racing to develop quantum-resistant security protocols before large-scale quantum computers make current encryption methods obsolete. Perhaps most intriguingly, quantum sensors that exploit entanglement are beginning to reveal previously hidden aspects of the physical world. By entangling the quantum states of many particles simultaneously, researchers can create measurement devices that surpass the fundamental limits of classical sensors under carefully controlled conditions. These quantum sensors can detect gravitational waves from distant black hole mergers, measure magnetic fields with unprecedented precision, and in experimental settings probe the quantum properties of biological systems. Some researchers speculate that quantum entanglement might play a role in biological processes themselves. While this remains highly speculative and no scientific consensus exists, preliminary studies have suggested that quantum effects might influence photosynthesis in plants, navigation in migrating birds, and have been theoretically discussed in relation to certain aspects of consciousness in the brain. These ideas remain controversial and unproven, but they hint at the possibility that life itself might have evolved to exploit quantum phenomena in limited and specific ways. As these technologies mature, they promise to reshape our relationship with information, computation, and measurement itself. The quantum internet of the future might connect not just classical computers, but quantum processors capable of sharing entangled states across continental distances in experimental and early deployment scenarios. Quantum sensors might reveal new phenomena in physics, chemistry, and biology by detecting correlations too subtle for classical instruments to observe. But the implications of entanglement extend far beyond practical applications. They challenge us to reconsider our most fundamental assumptions about the nature of reality itself. If particles can be connected across arbitrary distances, if measurement of one system can be found to correlate with another regardless of the space between them, Then what does this tell us about the structure of the universe? Different interpretations of quantum mechanics offer varying perspectives on these profound questions. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems don't have definite properties until they're measured. In this view, entangled particles don't possess hidden states that determine their behaviour. Instead, their properties are described as becoming definite at the moment of measurement, with the correlations between entangled particles emerging from the fundamental probabilistic nature of quantum reality. The many-worlds interpretation, proposed by Hugh Everett III, offers a radically different picture. Rather than accepting that measurements create definite outcomes from quantum uncertainties, this interpretation suggests that all possible outcomes actually occur, but in separate parallel universes according to the mathematical formalism of the theory. When you measure an entangled particle and find it in a particular state, you're not creating that outcome, but describing which branch of the multiverse you experience. The correlations between entangled particles arise because the branching process itself maintains consistent relationships across all the parallel realities. Hidden variable theories championed by Einstein and later developed by David Bohm propose that particles do have definite properties at all times, but these properties are governed by deeper variables that we cannot directly observe. In Bohm's interpretation, entangled particles remain connected through what he called the quantum potential, a non-local influence that guides their behaviour in ways that reproduce the predictions of quantum mechanics without violating experimental results, while maintaining a fundamentally deterministic universe. More recent interpretations focus on the role of information and observation in quantum phenomena. Some physicists argue that entanglement is fundamentally about information rather than physical properties. In this view, measuring an entangled particle doesn't change the particle itself, but updates the information available about the entire entangled system. The correlations arise from the way information flows through quantum systems, with entanglement representing a form of distributed information that cannot be localized to individual particles. These different interpretations remain subjects of active debate among physicists and philosophers of science. While they all make identical predictions about experimental results, they offer vastly different pictures of what quantum entanglement tells us about the nature of reality. Some suggest a universe where properties emerge from observation, others a multiverse where all possibilities coexist, still others a deterministic reality governed by hidden influences. What remains clear is that entanglement forces us to abandon simple, classical pictures of reality. The universe is not composed of separate, independent objects that interact only through local forces and signals. Instead, it appears to be a fundamentally interconnected system where distant events can be correlated in ways that transcend our everyday understanding of space and causality. As you reflect on these possibilities, consider how they might reshape your understanding of existence itself. If the particles that compose your body are fundamentally entangled with particles throughout the universe at the level of their quantum descriptions, if the boundaries between separate objects are less definite than they appear, if reality itself might be more unified and interconnected than our classical intuitions suggest, then what does this mean for how you relate to the world around you? These questions venture into territory where science meets philosophy, where empirical observation encounters the deepest mysteries of existence. Quantum entanglement doesn't provide easy answers to these profound questions, but it does offer hints that the universe might be far more interconnected and mysterious than we ever imagined. And in that mystery lies both the challenge and the wonder of continuing to explore the quantum landscape that underlies everything we know. The mathematics of entanglement reveals something even more extraordinary when we examine how these quantum connections persist across time itself. Scientists studying the temporal development of entangled states have discovered that these correlations can form and evolve on timescales so brief they challenge our understanding of causality itself. When particles interact and become entangled, the establishment of their quantum connection happens faster than almost any other process in nature, according to current experimental resolution, creating bonds that transcend not only space but our conventional understanding of time. Consider what this means for the fabric of reality. In the time it takes light to travel the width of a single atom, countless entangled pairs are forming and evolving throughout the universe. These quantum relationships are being woven into existence at every moment, creating an ever-changing tapestry of connections that spans from the subatomic realm to the cosmic scale. The universe isn't simply a collection of objects moving through empty space. It's a dynamic web of correlations, constantly forming new patterns of connection while maintaining others across vast distances and timescales. This temporal aspect of entanglement has led some researchers to explore whether quantum correlations might extend backward through time itself. While this remains highly speculative and no scientific consensus exists, preliminary theoretical work suggests that entanglement might be mathematically described as connecting not only distant locations, but potentially different moments in time. The implications would be staggering, suggesting that the quantum realm operates according to principles that transcend our linear understanding of past, present, and future. Recent advances in quantum technology have allowed scientists to probe these temporal mysteries with unprecedented precision. Using ultra-fast laser pulses and sophisticated detection systems, researchers can now observe the birth of entanglement in real time, watching as quantum correlations emerge from the interaction of particles and spread throughout quantum systems. These observations reveal entanglement as a process rather than a static phenomenon, something that actively shapes and reshapes the quantum landscape on timescales far shorter than human perception. As you contemplate these ideas, notice how they might shift your perception of time itself. The moment you're experiencing right now isn't isolated from other moments. In some theoretical descriptions, entanglement may relate events across time, suggesting that this present instant might be quantumly correlated with moments in the past and future within certain models. Your current thoughts and experiences might be part of a vast temporal web of connections that extends far beyond your immediate awareness. The study of quantum entanglement has also revealed unexpected connections between information theory and the fundamental structure of reality. Information, it turns out, cannot be destroyed in quantum systems, only transformed or redistributed. When entangled particles interact with their environment, their quantum correlations don't simply disappear. Instead, the information encoding their entangled state becomes distributed across larger and larger systems, eventually encompassing vast networks of particles. This principle, often discussed in the context of quantum information conservation, suggests that every quantum interaction leaves traces in the fabric of reality. The entangled states that existed in the early universe, formed in the first moments after the Big Bang, might still persist today in highly distributed and indirect forms. The universe, from this perspective, can be viewed as a vast quantum memory system, preserving information about every interaction that has ever occurred. Some interpretations suggest, though this remains unproven, that consciousness itself might emerge from the complex patterns of quantum information processing that occur in biological systems. While no scientific consensus exists on this topic, researchers continue to explore whether the strange properties of quantum mechanics might play a role in the emergence of awareness, memory, and subjective experience. These investigations remain speculative, but they hint at deep connections between the quantum realm and the phenomenon of consciousness that we experience directly. The practical implications of understanding quantum information are already reshaping technology. Quantum error correction, the process of protecting quantum information from environmental interference, has become one of the most active areas of research in quantum computing. By understanding how quantum information flows through entangled systems, engineers are developing methods to preserve and manipulate quantum states with extraordinary precision. These advances are leading toward the creation of large-scale quantum networks that could span continents or even the entire planet. Imagine a future where quantum entanglement connects not just laboratory experiments, but global communication systems, financial networks, and scientific instruments under tightly controlled conditions. Such quantum internet infrastructure would create channels of information exchange that are fundamentally more secure and potentially more powerful than anything possible with classical technology. As you reflect on these possibilities, consider how quantum entanglement might already be influencing your daily life in ways you never realized. The chemical reactions occurring in your body at every moment involve countless quantum interactions. The electronic devices you use depend on quantum mechanical effects in their semiconductors and processors. Even the light reaching your eyes from distant stars carries quantum information that has been preserved across billions of years of cosmic travel. The exploration of entanglement has also opened new windows into understanding the nature of space-time itself. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by mass and energy. But recent theoretical work suggests that quantum entanglement might play an even more fundamental role in shaping the geometry of space and time. Some physicists now propose that space-time emerges from the patterns of entanglement between quantum systems. In this view, the familiar 3 dimensions of space and 1 dimension of time aren't fundamental features of reality, but rather emergent properties that arise from deeper quantum correlations according to certain theoretical frameworks. Distance itself might be a manifestation of the degree of entanglement between different regions of the quantum field that underlies all existence. This idea, while still highly speculative, suggests a universe where space and time are not the stage upon which quantum events occur, but rather consequences of quantum entanglement itself. The separation you perceive between yourself and distant objects might reflect the limited entanglement between the quantum systems that compose your body and those that make up faraway regions of space. These theoretical developments are driving new experimental programs designed to test whether entanglement truly does shape the structure of space-time. Scientists are building increasingly sensitive instruments to detect tiny correlations in the quantum vacuum, the supposedly empty space between particles. Early results suggest that even this apparent nothingness is filled with quantum fluctuations and entangled states that might indeed contribute to the geometry of space and time. If these ideas prove correct, they would represent a complete revolution in our understanding of reality. The universe would not be composed of matter and energy moving through space and time, but rather of quantum information structures, with matter, energy, space and time all emerging as different aspects of underlying entanglement patterns. The philosophical implications of such a view are profound. If reality is fundamentally made of quantum information and entanglement, then the boundaries between self and environment, between observer and observed, become much more fluid than our classical intuitions suggest. You would not be a separate entity observing an external world, but rather one perspective within the flow of quantum information, intimately connected to everything else in the universe. These ideas connect quantum physics to ancient philosophical traditions that have long suggested the fundamental unity of all existence. While science cannot prove or disprove such metaphysical claims, the discoveries of quantum entanglement do seem to point toward a universe that is far more interconnected than the mechanical worldview that dominated scientific thinking for centuries. As you sit quietly and absorb these concepts, take a moment to sense your own participation in this quantum universe. The atoms in your body were forged in the nuclear furnaces of ancient stars, scattered through space by stellar explosions, and eventually gathered together to form the complex molecules that enable your existence. Throughout this cosmic journey, these particles have existed within quantum correlations with countless other systems throughout the universe. The oxygen you breathe carries quantum information from the photosynthetic processes that created it. The light reaching your eyes preserves quantum correlations established in the nuclear reactions that occurred in the sun's core 8 minutes ago. Even your thoughts and emotions emerge from patterns of neural activity that depend on quantum mechanical processes in the synapses and molecules of your brain. From this perspective, you are not separate from the universe, but rather deeply embedded within its quantum nature. Your awareness represents one possible way the universe reflects upon itself through the complex patterns of entanglement and information processing that compose your neural networks. This remains an interpretive viewpoint rather than an established scientific conclusion, but it illustrates how quantum entanglement might connect the deepest questions about consciousness with the fundamental nature of physical reality. The study of quantum entanglement continues to evolve rapidly, with new discoveries regularly challenging our understanding of how these mysterious correlations operate. Recent experiments have demonstrated entanglement between increasingly large and complex systems, from individual atoms to molecular complexes to microscopic mechanical devices. Each advance pushes the boundary between the quantum and classical worlds, revealing that the strange properties of entanglement can persist even in systems large enough to see with the naked eye. These developments are leading toward tests of quantum mechanics in entirely new regimes. Scientists are working to create entangled states involving living organisms, though this remains technically challenging and scientifically controversial. If successful, such experiments might reveal whether the quantum realm extends into biological systems in ways that could influence the processes of life itself. Other researchers are exploring whether entanglement might play a role in the structure of black holes, the mysterious regions of space-time where gravity becomes so strong that nothing, not even light, can escape. Theoretical work suggests that the information that falls into a black hole might remain entangled with radiation that escapes, creating connections that transcend the black hole's event horizon. These ideas remain highly speculative, but they hint at deep connections between quantum entanglement, gravity, and the nature of information itself. As you contemplate these frontiers of scientific exploration, Notice how they invite you to question the boundaries of what seems possible. The universe revealed by quantum entanglement is far stranger and more wonderful than anything imagined by earlier generations of scientists. Yet each new discovery, rather than solving the mystery of entanglement, seems to deepen it, revealing new layers of complexity and connection. The journey into quantum entanglement is ultimately a journey into the heart of mystery itself. Despite decades of experimental confirmation and technological application, we still don't fully understand how entangled particles maintain their correlations across space and time. We can predict the statistical behavior of entangled systems with extraordinary precision, but the mechanism underlying these correlations remains as puzzling as ever. Perhaps this enduring mystery is itself significant. Quantum entanglement seems to point toward aspects of reality that transcend human comprehension, suggesting that the universe operates according to principles that may always remain partially beyond our grasp. This doesn't diminish the value of scientific investigation, but rather reminds us of the profound humility required when confronting the deepest questions about existence. As our exploration of quantum entanglement draws toward a close, we find ourselves in a position similar to early explorers mapping unknown territories. We've documented the landscape of this quantum realm, charted its major features, and begun to understand how it connects to the familiar world of our everyday experience. Yet vast regions remain unexplored, and the map continues to reveal new territories that challenge our understanding. The phenomenon of quantum entanglement stands as perhaps the most compelling evidence that reality operates according to principles far stranger than our classical intuition suggest. Distance, which seems so fundamental to our everyday experience, no longer functions in the same way in the quantum realm. Particles separated by cosmic distances remain correlated in ways that transcend space and time. The universe reveals itself to be not a collection of separate objects, but a unified whole, where every part contains information about every other part within certain quantum frameworks and interpretations. This quantum unity doesn't erase the apparent separations of the classical world, but rather reveals them to be emergent properties arising from deeper quantum connections. The chair you're sitting on appears solid and separate from your body, yet both are composed of quantum fields whose fluctuations are correlated across space and time. The distinction between self and environment, while useful for navigating daily life, may be less fundamental than we typically assume. As you rest in this understanding, allow yourself to sense your participation in this quantum tapestry. You're not merely observing the universe from the outside, but experiencing it from within as one of its participants. Your thoughts and perceptions arise from the same quantum processes that govern the behavior of entangled particles. In a metaphorical sense, the universe is thinking and experiencing itself through your awareness. The practical applications of quantum entanglement will undoubtedly continue to transform technology and expand human capabilities. Quantum computers will solve problems beyond the reach of classical machines. Quantum communication networks will provide unprecedented security for information exchange. Quantum sensors will reveal previously hidden aspects of physical reality, but perhaps the greatest gift of quantum entanglement is the way it expands our sense of what's possible. In a universe where particles can be strongly correlated across arbitrary distances, where the act of measurement can be associated with distant outcomes, where space and time themselves might emerge from patterns of quantum correlation, our classical assumptions about limitation and separation need constant revision. The story of quantum entanglement is still being written. Each new experiment reveals additional layers of complexity and connection. Each technological application opens new possibilities for human interaction with the quantum realm. Each theoretical advance suggests new ways that consciousness, information, and physical reality might be interconnected. As you drift into whatever comes next, carry with you this sense of profound connection to the quantum universe that surrounds and includes you. In the gentle darkness behind your eyelids, quantum correlations are forming and dissolving at every instant. In the quiet spaces between your thoughts, the same quantum fields that enable entanglement are flickering with possibility. Whether you find yourself in dreams or in waking awareness, remember that you are always part of this vast quantum web, connected to every star, every particle, every moment that has ever existed or ever will exist. Distance, in the deepest conceptual sense, has indeed disappeared, leaving only the eternal dance of quantum correlation that weaves all existence into a single, magnificent whole. The boundaries between the quantum and classical worlds continue to blur as scientists push entanglement into increasingly exotic territories. Recent experiments have achieved quantum correlations between systems so different they seem to belong to entirely separate realms of physics. Researchers have successfully entangled the motion of tiny mechanical oscillators with the quantum states of individual photons, creating hybrid systems that bridge the gap between the tangible world of objects we can see and the invisible realm of quantum fields. These mechanical quantum systems represent something unprecedented in the history of science. Imagine a microscopic tuning fork, so small it contains only a few thousand atoms, vibrating in perfect quantum synchronization with a particle of light located elsewhere in the laboratory. When the photon's quantum state changes, the mechanical oscillator responds in a precisely correlated way, its physical motion shifting to maintain their entangled connection. The boundary between matter and energy, between the substantial and the ethereal, appears to dissolve into patterns of pure correlation that transcend our classical categories. What makes these experiments particularly remarkable is their scale. While early entanglement research focused on individual particles, like electrons or photons, these new systems involve collections of thousands or even millions of atoms moving together as a single quantum entity. The oscillators are large enough to be visible under a microscope, yet they maintain quantum correlations as delicate and mysterious as those between individual particles separated by vast distances. This progression toward larger entangled systems raises profound questions about where the quantum realm ends and the classical world begins. For decades, physicists assumed that quantum effects would inevitably disappear as systems became larger and more complex, overwhelmed by interactions with their environment. Yet each new experiment pushes this boundary further, revealing quantum behavior in systems of ever-increasing size and complexity. The implications extend far beyond laboratory curiosities. If quantum entanglement can persist in mechanical systems visible to the human eye, what prevents it from operating in even larger structures? Some interpretations suggest, though this remains unproven, that quantum correlations might subtly influence systems at scales we never previously considered quantum mechanical. This doesn't mean that everyday objects suddenly start tunneling through walls or existing in multiple states simultaneously, but it does suggest that the quantum realm might extend its influence into domains we traditionally considered purely classical. Consider the molecules in your body, the complex proteins that enable your cellular functions. the neural networks that generate your thoughts and memories. Each of these systems consists of countless atoms whose quantum states are constantly evolving and interacting. While the warm, noisy environment of biological systems generally destroys the delicate correlations required for observable quantum effects, recent research has begun to identify limited and highly specific exceptions where quantum phenomena might indeed play functional roles in living systems. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to exploit quantum coherence to achieve remarkable efficiency in energy transfer. When light strikes a leaf, the resulting excitation doesn't simply bounce randomly through the molecular machinery until it reaches the reaction center. Instead, some evidence suggests that quantum superposition allows the energy to explore multiple pathways simultaneously, finding the most efficient route through well-described quantum mechanical processes. This biological quantum mechanics remains an active area of research, with scientists carefully investigating which quantum effects, if any, persist in the complex environments found within living cells. The evidence suggests that evolution might have discovered ways to harness quantum phenomena for biological advantage, though the mechanisms remain poorly understood and controversial within the scientific community. As you contemplate these possibilities, notice how they might shift your perception of the relationship between mind and matter, between consciousness and the physical world. While no scientific evidence supports the idea that human thoughts or emotions directly control quantum systems, the discovery that quantum effects might operate within biological systems opens intriguing questions about the nature of awareness itself. The emergence of quantum biology has inspired researchers to investigate whether quantum entanglement might play a role in the most mysterious biological phenomenon of all, consciousness itself. This remains highly speculative territory, with no scientific consensus about whether quantum effects contribute meaningfully to neural function or subjective experience. However, the possibility has captured the imagination of scientists and philosophers alike, leading to careful investigations of quantum processes in the brain. Some theoretical frameworks suggest that the microtubules within neurons, the protein structures that help maintain cellular shape and transport materials, might serve as hypothetical quantum waveguides capable of maintaining coherent quantum states despite the warm, noisy environment of the brain. These ideas remain controversial and unproven, but they illustrate how the boundaries of quantum mechanics continue to expand into previously unimaginable territories. Other researchers focus on the role of quantum entanglement in the binding problem, the mysterious process by which the brain integrates information from different sensory modalities and neural regions into unified conscious experiences. While classical neural networks can certainly account for much of this integration, some interpretations suggest that quantum correlations have been proposed as a possible contributing mechanism, though this remains unconfirmed. These investigations into quantum consciousness remain at the frontier of both neuroscience and quantum physics, with most results still preliminary and subject to intense scientific debate. What seems clear is that consciousness emerges from the complex dynamics of neural networks, but whether quantum effects contribute meaningfully to these dynamics remains an open question that will require much more research to resolve. The exploration of quantum effects in biological systems has also led to investigations of whether meditation and contemplative practices might influence quantum processes in the brain or body. While this remains entirely speculative, Some researchers have begun to study whether states of deep meditation correlate with measurable changes in quantum coherence within biological systems. These studies face enormous technical challenges, as detecting quantum effects in warm biological systems requires extraordinarily sensitive instruments and careful experimental controls. Early results remain inconclusive, with some studies suggesting possible correlations while others find no measurable effects. The scientific consensus remains that extraordinary claims require extraordinary evidence, and the evidence for quantum effects in meditation remains far from extraordinary. Nevertheless, the contemplative traditions have long described experiences that seem to transcend ordinary boundaries between self and environment, between observer and observed. Practitioners often report profound states of interconnectedness that echo, at a metaphorical level, the non-local correlations revealed by quantum entanglement research. While these subjective experiences don't constitute scientific evidence for quantum effects in consciousness, they do suggest interesting parallels between the insights of contemplative practice and the discoveries of quantum physics. As you reflect on these connections, remember that metaphorical parallels don't establish causal relationships. The sense of unity described by contemplatives and the quantum correlations demonstrated by physicists might arise from entirely different mechanisms, yet both point toward a reality that transcends the simple, mechanistic worldview that dominated scientific thinking for centuries. The practical applications of quantum entanglement continue to evolve in directions that would have seemed impossible just decades ago. Quantum radar systems use entangled photons to detect objects with unprecedented sensitivity in experimental settings, while remaining nearly invisible to conventional detection methods. These systems exploit the fact that entangled photons maintain their correlations even when one member of the pair interacts with a distant target, allowing for detection schemes that are fundamentally more subtle than classical radar approaches in experimental implementations. Quantum sensing networks are beginning to span continental distances, with entangled atomic clocks providing time synchronization more precise than any classical system could achieve. These quantum timing networks will eventually enable new forms of navigation, communication, and scientific measurement that depend on extraordinarily precise coordination across vast distances under controlled conditions. The financial implications of quantum technologies are driving massive investments from governments and corporations worldwide. Companies are racing to develop quantum computers powerful enough to theoretically compromise current encryption schemes, while simultaneously creating new quantum cryptographic protocols that will remain secure even against quantum attacks. This quantum arms race is reshaping entire industries as organizations prepare for a future where classical security assumptions no longer apply. Medical applications of quantum sensing are revealing previously invisible aspects of biological function. Quantum magnetometers can detect the tiny magnetic fields produced by neural activity with sensitivity far exceeding classical instruments, potentially enabling new forms of brain imaging that could revolutionize neuroscience and medical diagnosis. These quantum medical devices remain experimental, but they hint at future possibilities where quantum sensitivity reveals biological processes currently hidden from observation. The integration of quantum technologies into everyday life proceeds gradually but inexorably. While you might not encounter quantum computers directly, the cryptographic protocols protecting your online communications are already being upgraded to resist quantum attacks. The GPS signals guiding your navigation depend on atomic clocks, whose precision emerges from quantum mechanical effects. Even the LED lights illuminating your environment operate through quantum processes that convert electrical energy into photons with remarkable efficiency. As these quantum technologies mature, they will likely become as invisible and essential as the classical technologies that currently surround you. The quantum realm isn't a separate domain that exists only in specialized laboratories. It's the deepest known physical layer of reality upon which all classical phenomena emerge, and our growing ability to harness quantum effects is simply bringing us into closer alignment with the way the universe actually operates. The theoretical foundations of quantum entanglement continue to evolve as physicists explore increasingly sophisticated mathematical frameworks for understanding these phenomena. Recent advances in quantum field theory have revealed deep connections between entanglement and the structure of space-time itself, suggesting that the geometry of space and time may, within certain theoretical models, emerge from patterns of quantum correlation rather than existing as fundamental features of reality in those frameworks. These theoretical developments challenge our most basic assumptions about the nature of existence. If space-time emerges from entanglement, then distance and duration are not fundamental properties but rather emergent features that arise from deeper quantum relationships. The separation you perceive between yourself and distant objects, the flow of time from past to future, even the apparent solidity of matter, could in these theoretical descriptions be understood as consequences of underlying entanglement patterns that operate according to principles we're only beginning to understand. Holographic theories of quantum gravity suggest that all the information contained within a volume of space can be encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional images on a flat surface. This holographic principle implies that the three-dimensional world of our experience might be mathematically describable as a projection of information stored on a distant boundary, with the entanglement providing the mechanism that correlates events throughout the interior volume within these theoretical constructions. These ideas remain highly speculative and mathematically complex, but they illustrate how quantum entanglement research is driving fundamental revisions to our understanding of reality itself. The universe revealed by quantum mechanics operates according to principles so foreign to our everyday experience that even physicists struggle to develop intuitive understanding of what their equations actually describe. Some interpretations suggest that information, rather than matter or energy, may be treated as the most fundamental constituent of reality within certain theoretical frameworks. In this view, particles, forces, space, and time are all emergent properties of underlying information processing systems, with entanglement representing the mechanism by which information becomes correlated across different regions of the computational substrate that underlies physical reality within these interpretive frameworks. This informational perspective on quantum mechanics connects to ancient philosophical traditions that have long suggested that mind or consciousness might be more fundamental than matter. While modern physics certainly doesn't prove such metaphysical claims, the discovery that information plays such a central role in quantum phenomena does open new possibilities for understanding the relationship between mind and matter, between subjective experience and objective reality. The experimental verification of quantum entanglement has also revealed unexpected connections between different areas of physics that were previously thought to be unrelated. Condensed matter physicists studying the electronic properties of exotic materials have discovered that quantum entanglement plays a crucial role in determining the behavior of high-temperature superconductors, materials that can conduct electricity without resistance at relatively warm temperatures. These discoveries suggest that entanglement might be the key to understanding and eventually designing new materials with precisely tailored properties. Imagine materials that could store and transmit energy with dramatically improved efficiency, substances that could change their properties in response to quantum signals, or structures that could maintain quantum coherence at room temperature under carefully controlled conditions. Such quantum materials could revolutionize everything from energy storage to medical devices to space exploration in principle, though many challenges remain. The study of quantum entanglement in many body systems has revealed phenomena that challenge our understanding of how complex systems can maintain quantum coherence. When thousands or millions of particles become entangled together, they can form collective quantum states that exhibit properties impossible for any individual particle. These quantum many-body systems can undergo phase transitions that have no classical analogue, transitioning between different types of entangled states in ways that reveal new forms of quantum order. Researchers have discovered quantum spin liquids, materials where magnetic moments remain in quantum superposition even at absolute zero temperature, maintaining patterns of entanglement that never freeze into classical arrangements. These exotic states of matter exist at the boundary between order and chaos, exhibiting quantum entanglement that persists across macroscopic distances while remaining fluid and dynamic at the microscopic scale. The implications for understanding the emergence of classical behavior from quantum foundations are profound. If large systems can maintain quantum entanglement under certain conditions, then the transition from quantum to classical behavior is not simply a matter of size, but depends on the specific ways that quantum systems interact with their environment. This suggests that there might be natural systems, perhaps in exotic astrophysical environments or in carefully engineered artificial structures, where quantum effects persist at scales previously thought impossible. As you contemplate these possibilities, consider how they might reshape your understanding of the relationship between simplicity and complexity, between individual components and collective behavior. The quantum realm reveals that emergence, the process by which simple components give rise to complex phenomena, operates according to principles far more subtle and interconnected than classical physics suggested. Your own existence represents one of the most remarkable examples of quantum emergence in the known universe. The consciousness that allows you to contemplate these ideas arises from the collective behavior of billions of neurons, each of which emerges from the quantum mechanical interactions of countless atoms and molecules. While we don't yet understand the mechanisms by which quantum processes give rise to classical neural function, or how neural networks generate subjective experience, the mere fact that such emergence occurs demonstrates the extraordinary creative power often discussed in relation to quantum entanglement. The future of quantum entanglement research promises discoveries that will likely surprise even the scientists working at the cutting edge of these investigations. Planned experiments will test entanglement between increasingly exotic systems, between light and matter, between different phases of matter, between quantum systems and gravitational fields, and possibly even between laboratory systems and cosmic structures. Space-based quantum experiments are beginning to test entanglement across truly astronomical distances, with satellites creating and maintaining quantum correlations between ground stations separated by continents. These experiments not only demonstrate the robustness of quantum entanglement, but also open the possibility for global quantum communication networks that could enable forms of coordination and collaboration impossible with classical technology. The search for quantum gravity, the long-sought theory that will unite quantum mechanics with Einstein's general relativity, increasingly focuses on the role of entanglement in shaping the structure of space-time itself. Future gravitational wave detectors might be sensitive enough to observe quantum effects in the fabric of space and time, revealing whether the oscillations that ripple across the cosmos maintain quantum correlations across cosmic distances under future experimental conditions. These investigations venture into territory where the boundaries between physics, philosophy, and even spirituality become increasingly difficult to maintain. When scientists study the fundamental nature of space, time, matter, and information, they inevitably encounter questions that have occupied human contemplation for millennia. What is the nature of existence? How does consciousness arise from matter? What is the relationship between the observer and the observed? Quantum entanglement doesn't provide definitive answers to these ancient questions, but it does offer new perspectives that enrich our contemplation of them. The discovery that reality operates according to principles of non-local correlation and quantum superposition suggests that our ordinary experience of separation and definiteness might be approximations that emerge from deeper levels of interconnection and possibility. Some interpretations suggest, though this remains entirely speculative, that the sense of individual identity that seems so fundamental to human experience might itself be an emergent property of quantum information processing systems within certain philosophical or theoretical models. If consciousness arises from patterns of quantum correlation within neural networks, then the boundary between self and environment, between observer and observed, becomes much more fluid than our everyday experience suggests. This perspective doesn't diminish the reality or importance of individual experience, but rather places it within a larger context of cosmic interconnection. You remain a unique center of awareness, with your own thoughts, feelings, and perceptions, but these individual characteristics emerge from participation in quantum processes that connect you intimately with the rest of the universe. The contemplation of quantum entanglement naturally leads to reflections on the nature of love, compassion, and human connection. While no scientific evidence suggests that emotional bonds create quantum entanglement between human beings, the parallels are striking enough to inspire contemplation. Both quantum entanglement and emotional connection transcend ordinary boundaries, creating correlations that persist despite physical separation, influencing the behavior of connected systems in ways that seem to defy classical explanation. The metaphorical connections between quantum entanglement and human relationships have inspired artists, poets, and contemplatives to explore new ways of understanding intimacy and connection. These explorations remain firmly in the realm of metaphor and subjective experience rather than scientific fact, but they illustrate how quantum discoveries can enrich our understanding of human experience, even when they don't directly apply to it. As quantum technologies become more prevalent, they will likely influence not only our practical capabilities, but also our conceptual frameworks for understanding ourselves and our relationships. Growing up in a world where quantum communication and quantum computing are commonplace might naturally lead to ways of thinking about connection, information, and possibility that differ significantly from those shaped by purely classical technologies. The study of quantum entanglement continues to reveal new aspects of reality that challenge our assumptions about the possible and the impossible. Recent theoretical work suggests that quantum correlations might extend beyond the familiar realm of particles and fields into domains we haven't yet learned to observe directly. Some interpretations propose that consciousness itself might be a manifestation of quantum information processing, though this remains highly speculative and unproven. Other research explores whether quantum entanglement might play a role in biological evolution, with some theories suggesting that quantum effects could influence genetic mutations and epigenetic changes in ways that affect the direction of evolutionary development. These ideas remain at the very edge of scientific respectability, requiring much more research before they can be considered anything more than intriguing possibilities. The intersection of quantum mechanics with complexity theory has revealed that entangled systems can exhibit forms of self-organization and pattern formation that have no classical analogues. These quantum complex systems might provide insights into how order emerges from apparent chaos, how information flows through networks, and how collective behaviors arise from individual interactions. Such discoveries suggest that the universe might be far more creative and self-organizing than classical physics implied. If quantum entanglement enables forms of coordination and information sharing that transcend classical limitations, then the emergence of complex structures, from galaxies to living organisms to conscious beings, might involve quantum processes operating at scales and in contexts we're only beginning to investigate. As you rest in contemplation of these possibilities, allow yourself to sense your own participation in this vast web of quantum correlation as a metaphorical way of appreciating physical interconnectedness that spans from the subatomic realm to cosmic scales. The very act of contemplation involves quantum processes in your neural networks, patterns of entanglement, and information flow that enable the emergence of thoughts, insights, and understanding. Your awareness can be understood, in a philosophical sense, as one of the universe's ways of knowing itself, a temporary but precious convergence of matter, energy, and information that enables subjective experience to arise from objective quantum processes. This emergence of consciousness from quantum foundations remains one of the deepest mysteries in all of science, but it demonstrates the extraordinary creative potential often discussed in relation to quantum entanglement. The future will undoubtedly bring discoveries that will reshape our understanding of quantum entanglement in ways we cannot currently anticipate. Each new experiment reveals additional layers of complexity and connection. Each technological application opens new possibilities for human interaction with the quantum realm. Each theoretical advance suggests new ways that mind, matter, and information may be interconnected. The journey into quantum entanglement is ultimately a journey into the heart of mystery itself, an exploration of the deepest principles that govern the existence of everything from the smallest particles to the largest structures in the cosmos. These principles operate whether we understand them or not, weaving the fabric of reality according to rules that transcend human comprehension, while simultaneously enabling the emergence of beings capable of contemplating their own existence. As you continue to drift through these quantum landscapes of possibility and connection, remember that you are not merely observing the universe from the outside, but experiencing it from within, as a conscious system shaped by physical processes. The quantum correlations that enable entanglement are not separate from you, but constitute part of the physical foundations underlying your being, the substrate from which your thoughts and experiences arise. In the gentle darkness that surrounds you now, Quantum fields fluctuate with possibilities that extend throughout space and time. The particles that compose your body maintain correlations with systems throughout the cosmos, connections that transcend distance and duration, weaving you into the vast tapestry of existence that encompasses everything that has ever been or ever will be. Ever been or ever will be. The philosophical implications of quantum entanglement extend far beyond the laboratory walls where these phenomena are studied. When you truly contemplate what entanglement means for the nature of reality, you begin to realize that it challenges some of our most fundamental assumptions about existence itself. The classical worldview that dominated human thinking for centuries portrayed the universe as a vast machine made of separate, independent parts. Objects had definite properties, causes preceded effects in orderly sequences, and information travelled through space at finite speeds according to well-understood rules. Quantum entanglement challenges this orderly picture profoundly. It reveals a universe where separation may not be as fundamental as it appears, where distant events can be correlated in ways that transcend our everyday understanding of cause and effect, where the very act of gaining knowledge about one system can instantaneously affect another system, regardless of the space between them. This isn't simply a quirk of subatomic particles that has no bearing on our daily lives. It's a fundamental feature of reality that operates within the framework of quantum physics, from the quantum realm to the cosmos itself. Consider what this means for your own existence. The atoms that compose your body were forged in stellar furnaces billions of years ago, scattered across space by cosmic explosions, and eventually gathered together to form the complex molecules that enable life. Throughout this vast journey, these particles have maintained chains of interaction and correlation with countless other systems throughout the universe. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it connected through invisible threads of quantum correlation that stretch back to the birth of the cosmos. Some interpretations suggest, though this remains highly speculative and unproven, that consciousness itself has been hypothesized as a manifestation of quantum information processing. While no scientific consensus exists on this topic, the possibility opens intriguing questions about the relationship between mind and matter. If awareness emerges from patterns of quantum correlation within neural networks, then the boundary between observer and observed becomes much more fluid than our classical intuitions suggest. The measurement problem in quantum mechanics reveals the mysterious role that observation plays in determining reality. When you measure a quantum system, something profound happens that we still don't fully understand. The system transitions from a state of quantum superposition, where multiple possibilities exist simultaneously, to a definite classical state with well-defined properties. This transition, known as wave function collapse, occurs as described in certain interpretations. Yet the mechanism underlying this process remains one of the deepest mysteries in physics. Different interpretations of quantum mechanics offer radically different pictures of what actually happens during measurement. The Copenhagen interpretation suggests that quantum systems don't have definite properties until they're observed, implying that measurement itself, rather than consciousness alone, plays a fundamental role in defining outcomes. The many worlds interpretation proposes that all possible outcomes actually occur in parallel universes, with observation simply determining which branch of reality you experience. Hidden variable theories attempt to preserve classical realism by proposing deeper layers of reality that determine quantum outcomes according to deterministic rules. Each of these interpretations has profound philosophical implications. If the Copenhagen view is correct, then consciousness may appear to play a fundamental role in shaping the physical world, though this doesn't mean that thoughts directly control reality in any magical sense. If many worlds is accurate, then every possible version of history actually unfolds somewhere in the vast multiverse, with countless parallel versions of yourself experiencing different outcomes. If hidden variables exist, then the universe might be deterministic after all, operating according to deeper principles that we haven't yet discovered. What remains clear across all interpretations is that quantum mechanics forces us to abandon naive realism, the assumption that the world exists in definite states independent of observation. Reality at the quantum level is far more subtle and interconnected than our everyday experience suggests. Properties like position, momentum, and spin don't exist as definite attributes until they're measured. Instead, they exist as potentials, as probability clouds that only crystallize into definite values when the system interacts with measuring apparatus. This quantum view of reality has profound implications for how we understand knowledge itself. In the classical worldview, learning about the world was simply a matter of discovering pre-existing facts about how things are. Quantum mechanics suggests a more participatory universe, where the act of observation plays an active role in determining what becomes real. You're not simply a passive observer of an independent reality, but an observer interacting with physical processes that continuously shape observable outcomes. As you reflect on these ideas, take a moment to consider how they might reshape your understanding of your own role in the universe. You're not separate from the cosmic processes you're contemplating, but intimately woven into them. Your thoughts arise from quantum processes in your brain. Your perceptions emerge from quantum interactions between light and matter. Even your sense of being a distinct individual might be understood as a temporary pattern in the flow of quantum information that extends throughout the cosmos. The study of quantum entanglement has also revealed unexpected connections between information theory and the fundamental structure of reality. Information, it turns out, plays a much more central role in physics than anyone anticipated when quantum mechanics was first developed. The famous physicist John Wheeler captured this insight in his phrase, "it from bit," suggesting that physical reality might emerge from underlying information processing rather than the other way around. This informational view of reality connects quantum mechanics to ancient philosophical traditions that have long suggested mind or consciousness might be more fundamental than matter. While modern physics certainly doesn't prove such metaphysical claims, the discovery that information plays such a crucial role in determining physical outcomes does open new possibilities for understanding the relationship between subjective experience and objective reality. Quantum entanglement demonstrates that information can be non-local, existing in correlations between distant systems, rather than being localized in any particular place. When two particles are entangled, the information about their combined state cannot be assigned to either particle individually. Instead, it exists in the relationship between them, in patterns of correlation that transcend spatial separation. This suggests that reality itself might be fundamentally relational, built from networks of information and correlation rather than from independent objects with intrinsic properties. The implications for understanding consciousness are intriguing, though they remain highly speculative. If awareness emerges from information processing in the brain, and if quantum entanglement enables forms of information sharing that transcend classical limitations, then consciousness has been hypothesized to involve quantum correlations that connect different regions of neural networks in ways that classical neuroscience cannot fully account for. This remains an open question in neuroscience, with some researchers exploring quantum theories of consciousness, while others remain skeptical that quantum effects could persist in the warm, noisy environment of biological systems. Recent research has begun to explore whether contemplative practices, like meditation, might influence quantum processes in the brain or body, though this remains entirely speculative and unproven. Some studies have suggested possible correlations between meditative states and changes in neural coherence, but whether these changes involve genuinely quantum mechanical effects remains unclear. The scientific consensus maintains that extraordinary claims require extraordinary evidence, and the evidence for quantum effects in meditation practices remains far from conclusive. Nevertheless, the phenomenology of contemplative experience often describes states of awareness that transcend ordinary boundaries between self and environment, between observer and observed. Practitioners frequently report profound experiences of interconnectedness that resonate at a metaphorical level with the non-local correlations revealed by quantum entanglement research. While these subjective experiences don't constitute scientific evidence for quantum effects in consciousness, they do suggest interesting parallels between the insights of contemplative practice and the discoveries of quantum physics. The practical applications of quantum entanglement continue to expand in directions that promise to transform human civilization in fundamental ways. Quantum computing represents perhaps the most revolutionary application, with the potential to solve certain problems exponentially faster than any classical computer could manage. These quantum computational advantages arise directly from entanglement, which allows quantum systems to explore vast numbers of possible solutions simultaneously, rather than checking them one by one. The implications for fields like cryptography, drug discovery, materials science, and artificial intelligence are staggering. Quantum computers could break most current encryption schemes while simultaneously enabling new forms of quantum cryptography that are fundamentally unbreakable. They could simulate molecular interactions with unprecedented theoretical accuracy, enabling the design of new medications and materials with precisely tailored properties. They might even provide new insights into the nature of intelligence itself, revealing whether quantum effects play any role in the emergence of consciousness and creativity. Quantum communication networks are beginning to span global distances using entangled photons to create channels of information exchange that are secured by the laws of physics themselves. Any attempt to intercept or eavesdrop on these quantum communications necessarily disturbs the entangled correlations, immediately alerting users to security breaches. These quantum internet protocols will eventually enable forms of coordination and collaboration that are impossible with classical communication systems. The development of quantum sensors exploiting entanglement promises to reveal previously hidden aspects of physical reality. These devices can detect gravitational waves from distant cosmic events, measure magnetic fields with unprecedented precision, and probe the quantum properties of biological systems. Some researchers speculate that quantum sensors might eventually become sensitive enough to detect subtle correlations related to neural activity, potentially providing new windows into the relationship between consciousness and quantum mechanics. As these quantum technologies mature and become integrated into everyday life, they will likely influence not only our practical capabilities, but also our conceptual frameworks for understanding reality itself. Growing up in a world where quantum effects are harnessed for practical purposes might naturally lead to ways of thinking about connection, information, and possibility that differ significantly from those shaped by purely classical technologies. The exploration of quantum entanglement also opens new perspectives on some of humanity's most enduring questions about the nature of free will and determinism. Classical physics painted a picture of a deterministic universe where every event was the inevitable consequence of prior causes. Quantum mechanics introduces genuine randomness into the foundations of reality, with measurement outcomes that are fundamentally unpredictable, even in principle. This quantum indeterminacy might provide the kind of causal openness that some philosophers believe is necessary for genuine free will to exist. However, the relationship between quantum mechanics and free will remains deeply controversial among philosophers and scientists. Random events are not the same as freely chosen actions, and it's unclear whether quantum indeterminacy provides the right kind of causal openness to support meaningful notions of responsibility and choice. Some interpretations suggest that consciousness might be able to influence quantum processes in limited theoretical models, but this remains entirely speculative and lacks scientific support. What seems clear is that quantum mechanics reveals a universe that is neither fully deterministic nor completely random, but operates according to principles that transcend these classical categories. The future emerges from a complex interplay of quantum possibility and classical constraint, with measurement and observation playing crucial roles in determining which potential futures become actual. This suggests a participatory universe in an observational sense, though the exact mechanisms remain mysterious. The implications extend to questions about the nature of time itself. Quantum entanglement appears to operate outside our normal understanding of temporal sequence, with correlations that transcend not only spatial separation, but potentially temporal separation as well. Some interpretations of quantum mechanics suggest that the future might influence the past in ways that challenge our linear understanding of causation. These ideas remain highly speculative, but they illustrate how quantum discoveries continue to challenge our most basic assumptions about the nature of reality. Recent theoretical work has explored whether quantum entanglement might provide insights into the nature of consciousness and the hard problem of subjective experience. While no scientific consensus exists on these topics, some researchers have proposed that the unity of consciousness, the way that diverse sensory inputs and mental processes become integrated into a single, coherent experience, might involve quantum correlations that bind different regions of the brain into unified conscious states. This approach to understanding consciousness remains highly controversial and unproven, but it illustrates how quantum entanglement research might eventually shed light on some of the deepest mysteries of human existence. If consciousness does emerge from quantum information processing in the brain, then the study of entanglement might provide new tools for understanding not only how awareness arises from neural activity, but also how subjective experience relates to the objective physical world. As you contemplate these possibilities, notice how they might shift your sense of agency and responsibility in the world. If the universe operates according to quantum principles that transcend classical determinism, if consciousness plays a participatory role in shaping reality through observation and choice, if your awareness represents a meaningful perspective within the cosmic process, then your thoughts, decisions, and actions might carry significance that extends far beyond their immediate practical consequences. This doesn't mean that consciousness directly controls quantum events, or that positive thinking can manifest desired outcomes in any magical sense. The relationship between mind and quantum mechanics, if it exists at all, operates according to subtle principles that we're only beginning to investigate. What it might mean is that your participation in the universe is more significant and interconnected than classical physics suggested, that your consciousness represents a genuine contribution to the ongoing unfolding of reality rather than simply a passive observation of predetermined events. The future of quantum entanglement research promises discoveries that will likely transform our understanding of reality in ways we cannot currently anticipate. Planned experiments will test entanglement across increasingly exotic scales and conditions, from subatomic particles to astronomical distances, from laboratory environments to cosmic phenomena. Each new discovery has the potential to reveal additional layers of quantum interconnection that challenge our assumptions about the possible and the impossible. Space-based quantum experiments are beginning to test whether entanglement can persist across truly astronomical distances, with satellites creating and maintaining quantum correlations between ground stations separated by continents. These experiments will eventually extend to interplanetary and potentially interstellar scales, testing whether the quantum connections that seem so fundamental to reality operates consistently throughout the cosmos. The search for quantum gravity, the long-sought theory that will unite quantum mechanics with Einstein's general relativity, increasingly focuses on the role of entanglement in shaping the structure of spacetime itself. Some theoretical frameworks suggest that space and time emerge from patterns of quantum entanglement rather than existing as fundamental features of reality. If these ideas prove correct, they would represent a complete revolution in our understanding of the cosmos, revealing that even the stage upon which all events occur is itself a consequence of quantum correlation. These investigations venture into territory where the boundaries between physics, philosophy, and spirituality become increasingly difficult to maintain. When scientists study the fundamental nature of space, time, matter, and consciousness, they inevitably encounter questions that have occupied human contemplation for millennia. Quantum entanglement doesn't provide definitive answers to these ancient mysteries, but it does offer new perspectives that enrich our contemplation of them. The discovery that reality operates according to principles of non-local correlation and quantum superposition suggests that our ordinary experience of separation and definiteness might be approximations that emerge from deeper levels of interconnection and possibility. This perspective doesn't diminish the reality or importance of individual experience, but rather places it within a larger context of cosmic interconnection and creative potential. As quantum technologies become more prevalent in daily life, they will likely influence not only our practical capabilities, but also our cultural and spiritual frameworks for understanding ourselves and our place in the universe. The generation growing up with quantum computers, quantum communication, and quantum sensors, as commonplace technologies, might naturally develop ways of thinking about reality that are more comfortable with uncertainty, non-locality, and fundamental interconnection. The contemplation of quantum entanglement naturally leads to reflections on the nature of love, compassion, and human connection. While no scientific evidence suggests that emotional bonds create quantum entanglement between human beings, the parallels are striking enough to inspire thoughtful consideration. Both quantum correlations and emotional connections transcend ordinary boundaries, creating relationships that persist despite physical separation and influence the behavior of connected systems in ways that seem to defy simple explanation. These parallels remain firmly in the realm of metaphor and subjective experience rather than scientific fact. But they illustrate how quantum discoveries can enrich our understanding of human relationships, even when they don't directly apply to them. The universe revealed by quantum mechanics is far more interconnected and mysterious than classical physics suggested, and this expanded view of reality naturally invites expanded ways of thinking about connection, empathy, and care. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. The study of quantum entanglement continues to reveal new aspects of reality that challenge our assumptions about the nature of existence itself. Recent discoveries have shown that entanglement can persist in systems far larger and more complex than anyone previously imagined. From collections of thousands of atoms to mechanical devices visible under microscopes, each advance pushes the boundary between the quantum and classical worlds, revealing that the strange properties of entanglement can manifest even in systems that approach the scale of everyday experience. These developments suggest that the quantum realm might extend its influence into domains we never previously considered quantum mechanical. This doesn't mean that everyday objects suddenly start existing in multiple states simultaneously or tunneling through walls, but it does imply that quantum effects might play subtle but significant roles in systems we traditionally considered purely classical. The implications for understanding the emergence of classical reality from quantum foundations are profound. If quantum entanglement can persist in large, complex systems under certain conditions, then the transition from quantum to classical behavior depends not simply on size, but on the specific ways that quantum systems interact with their environment. This suggests that there might be natural or artificially created conditions where quantum effects persist at scales previously thought impossible. Your own existence represents one of the most remarkable examples of emergence in the known universe. The consciousness that allows you to contemplate these ideas arises from the collective behavior of billions of neurons, each of which emerges from quantum mechanical interactions between countless atoms and molecules. While we don't yet understand the mechanisms by which quantum processes give rise to neural function, or how neural networks generate subjective experience, the mere fact that such emergence occurs demonstrates the extraordinary creative potential inherent in quantum systems. The relationship between complexity and consciousness remains one of the deepest mysteries in science. Some interpretations suggest, though this remains entirely speculative, that awareness might emerge from specific patterns of quantum entanglement within neural networks, patterns that create the unified field of experience that characterizes conscious awareness. These ideas require much more research before they can be considered anything more than intriguing possibilities, but they illustrate how quantum entanglement research might eventually illuminate the nature of consciousness itself. The exploration of quantum effects in biological systems has revealed that life might have evolved to exploit quantum phenomena in ways that were previously unimaginable. Photosynthesis in plants appears to use quantum coherence to achieve remarkable efficiency in energy transfer, with excitation energy exploring multiple pathways simultaneously through quantum mechanical means. Migratory birds might use quantum entanglement in specialized proteins to detect magnetic fields with extraordinary sensitivity. These discoveries suggest that the boundary between the quantum and classical worlds is far more porous than scientists once believed. Evolution, it seems, may have discovered ways to harness quantum effects for biological advantage, creating living systems that operate at the interface between quantum possibility and classical reality. While most quantum effects are quickly destroyed by the warm, noisy environment of biological systems, life appears to have found ways to protect and exploit certain quantum phenomena. The implications for understanding the nature of life itself are staggering. If biological systems can maintain quantum coherence under certain conditions, then the processes of life may involve quantum effects that classical biology cannot fully account for. This doesn't mean that consciousness or biological function depends entirely on quantum mechanics, but it does suggest that quantum effects might play supporting or facilitating roles in the emergence and maintenance of living systems. As you reflect on these possibilities, consider how they might change your understanding of your own nature. Your body is not simply a classical mechanical system, but can be understood as a quantum biological system that maintains its organization through constant interaction with quantum fields and forces. The chemical reactions that power your cells, the neural processes that generate your thoughts, even the genetic mechanisms that maintain your identity all emerge from quantum mechanical foundations. This quantum biological perspective doesn't diminish your individuality or agency, but rather reveals them as emergent properties of extraordinarily complex physical systems. You remain a unique center of awareness and choice, but these classical properties emerge from participation in quantum processes that connect you intimately with the rest of the universe. The philosophical implications of quantum entanglement extend beyond questions about consciousness and biology to fundamental issues about the nature of reality itself. If particles can be genuinely connected across arbitrary distances, if measurement plays an active role in determining what becomes real, if information and correlation are more fundamental than matter and energy, then our basic categories for understanding existence require substantial revision. Some interpretations suggest that the universe might be fundamentally informational rather than material, with matter and energy emerging as different aspects of underlying information processing systems. In this view, quantum entanglement represents one proposed mechanism by which information becomes correlated across different regions of the computational substrate that underlies physical reality. This informational perspective on quantum mechanics connects to ancient philosophical traditions that have long suggested that mind or consciousness might be more fundamental than matter. While modern physics certainly doesn't prove such metaphysical claims, the discovery that information plays such a central role in quantum phenomena does open new possibilities for understanding the relationship between subjective experience and objective reality. The contemplation of these ideas naturally leads to questions about the nature of meaning and purpose in a quantum universe. If reality emerges from patterns of quantum correlation and information processing, if consciousness is interpreted by some as the universe becoming aware of itself through complex physical systems, if the boundaries between observer and observed are less definite than classical physics suggested, then human existence might be viewed as playing a more significant role in cosmic evolution than mechanistic worldviews implied. This doesn't mean that humans are the center of the universe, or that consciousness controls reality in any direct sense. Rather, it suggests that awareness and choice may represent meaningful factors in the ongoing evolution of cosmic structure and organization. Your thoughts and decisions, emerging as they do from physical processes in your neural networks, could be understood as contributing to the universe's capacity for self-organization and creative development. The future will undoubtedly bring discoveries that will reshape our understanding of quantum entanglement in ways we cannot currently anticipate. Each new experiment reveals additional layers of complexity and connection. Each technological application opens new possibilities for human interaction with the quantum realm. Each theoretical advance suggests new ways that mind, matter, and information might be interconnected. The journey into quantum entanglement is ultimately a journey into the heart of mystery itself, an exploration of principles that operate whether we understand them or not, weaving the fabric of reality according to rules that transcend human comprehension, while simultaneously enabling the emergence of beings capable of contemplating their own existence. As you continue to rest in contemplation of these profound mysteries, remember that you are not merely observing the universe from the outside, but experiencing it from within, as a conscious system shaped by physical law. The quantum correlations that enable entanglement are not separate from you, but constitute part of the foundation of your being, the substrate from which your thoughts, perceptions, and experiences arise. In this gentle darkness that surrounds you now, quantum fields fluctuate with possibilities that extend throughout space and time. The particles that compose your body maintain correlations with systems throughout the cosmos, connections that transcend distance and duration, weaving you into the vast tapestry of existence that encompasses everything that has ever been or ever will be. When distance disappears, as it does mathematically in quantum descriptions of entanglement, what remains is a network of relationships described by physical law, pure connection, pure possibility. You are not separate from this quantum universe, but woven into its very essence, a temporary but precious pattern in the ongoing interplay of correlation and consciousness, as described in philosophical interpretations of reality. The practical implications of quantum entanglement extend far beyond the specialized laboratories where these phenomena are first observed. As you rest in contemplation of these mysteries, consider how entanglement might already be shaping technologies you encounter in your daily life, often in ways so subtle you never notice their quantum foundations. The GPS system that guides your navigation relies on atomic clocks whose extraordinary precision emerges from quantum mechanical effects. These clocks measure time by counting the oscillations of atoms as they transition between energy levels, a process that depends entirely on the quantum nature of matter. Without the precision enabled by quantum mechanics, your GPS would accumulate errors of several miles within a single day, making modern navigation impossible. The LED lights illuminating your environment operate through quantum processes that convert electrical energy directly into photons with remarkable efficiency. When electrons and holes recombine in the semiconductor material, they release energy in precise quantum packages that correspond to specific colors of light. This quantum emission process allows LEDs to produce light with very little waste heat, revolutionizing everything from home lighting to display screens. Even the hard drives storing information in your computer exploit quantum effects. The giant magnetoresistance phenomenon that enables modern hard disk storage depends on quantum mechanical interactions between electrons with different spin orientations. These quantum spin effects allow engineers to pack enormous amounts of information into incredibly small spaces, enabling the digital revolution that has transformed human communication and knowledge sharing. But perhaps most remarkably, quantum entanglement is beginning to enable entirely new categories of technology that have no classical analogues. Quantum key distribution systems already protect sensitive communications for banks and government agencies, using the fragility of entangled states to detect any attempt at eavesdropping. These systems represent the first commercial applications of quantum entanglement, transforming the abstract mysteries of quantum correlation into practical tools for information security. The development of quantum computers represents perhaps the most revolutionary application of entanglement principles. Unlike classical computers that process information sequentially, quantum computers can explore multiple solutions simultaneously by maintaining quantum superpositions and entangled correlations between their processing elements. This quantum parallelism enables certain calculations that would take classical computers longer than the age of the universe to complete. Pharmaceutical companies are already using early quantum computers to simulate molecular interactions with high theoretical fidelity. These quantum simulations can model the behavior of drug molecules in ways that classical computers cannot match, potentially accelerating the discovery of new treatments for diseases that have long resisted therapeutic intervention. The quantum advantage emerges directly from entanglement, which allows quantum computers to represent and manipulate the complex correlations that govern molecular behavior. Materials scientists are exploring how quantum computers might enable the design of entirely new substances with precisely tailored properties. Imagine materials that could conduct electricity with zero resistance at room temperature, substances that could store vast amounts of energy in compact forms, or structures that could repair themselves when damaged. Such quantum-designed materials could revolutionize everything from energy storage to space exploration to medical devices. The field of quantum sensing is revealing previously invisible aspects of the physical world by exploiting entangled states to achieve measurement precision that surpasses fundamental classical limits. These quantum sensors can detect gravitational waves from distant black hole mergers, measure magnetic fields produced by neural activity under experimental conditions, and probe the quantum properties of biological molecules with extraordinary sensitivity. Medical applications of quantum sensing promise to revolutionize diagnosis and treatment by revealing biological processes that remain hidden from classical instruments. Quantum magnetometers can detect the tiny magnetic fields produced by neural activity, potentially enabling new forms of brain imaging that could transform neuroscience and psychiatry. These quantum medical devices remain largely experimental, but they hint at future possibilities where quantum sensitivity reveals previously invisible aspects of health and disease. As these quantum technologies mature, they will likely become as invisible and essential as the classical technologies that currently surround you. You might never directly interact with a quantum computer, but the cryptographic protocols protecting your online communications are already being upgraded to resist quantum attacks. The precision timing networks that synchronize global financial systems increasingly rely on quantum-enhanced atomic clocks. Even the fundamental research that expands human knowledge depends more and more on quantum sensors capable of detecting phenomena too subtle for classical instruments to observe. The integration of quantum technologies into everyday life proceeds gradually but inexorably, bringing us into closer alignment with the fundamental quantum nature of reality itself. The classical world of our everyday experience emerges from quantum foundations, and our growing ability to harness quantum effects simply makes this underlying reality more accessible and useful for human purposes. As you contemplate these practical applications, notice how they bridge the gap between the abstract mysteries of quantum entanglement and the concrete challenges of human existence. The same non-local correlations that puzzled Einstein are now enabling secure communications across continents. The same quantum superpositions that create measurement paradoxes are now powering computational advantages that could help address humanity's most complex problems. This transformation of mystery into utility doesn't diminish the wonder of quantum entanglement, but rather demonstrates the extraordinary creativity inherent in the universe's fundamental structure. The cosmos has organized itself in ways that not only permit but actively encourage the emergence of complex systems capable of understanding and exploiting their own quantum nature. Recent advances in quantum error correction have brought large-scale quantum computing much closer to practical reality. The challenge of maintaining quantum coherence in the face of environmental interference has driven the development of sophisticated techniques for protecting and manipulating quantum information. These error correction protocols exploit redundancy and entanglement to preserve quantum states, even when individual components of the system experience errors or decoherence. The mathematics underlying quantum error correction reveals deep connections between information theory, topology, and quantum mechanics. Some error correction codes create topological quantum states that are inherently protected from certain types of errors, suggesting that the geometry of quantum information might play a fundamental role in determining which quantum computations can be performed reliably. These topological quantum computers could eventually enable quantum calculations that remain stable for extended periods, opening new possibilities for solving complex optimization and simulation problems. The race to develop fault-tolerant quantum computers is driving innovations that extend far beyond computing itself. The techniques developed for controlling and manipulating quantum systems are finding applications in quantum sensing, quantum communication, and fundamental physics research. The precision required for quantum error correction is pushing the development of new materials, new fabrication techniques, and new measurement technologies that have applications throughout science and engineering. Consider how this quantum technology revolution might reshape human civilization over the coming decades. Quantum computers could enable the simulation of complex chemical reactions with previously unattainable accuracy, accelerating the development of new catalysts for capturing carbon dioxide from the atmosphere or converting sunlight into clean fuels. Quantum sensors could detect dark matter particles that have eluded detection for decades, revealing new aspects of cosmic structure and evolution. Quantum communication networks could create global channels of information exchange that are fundamentally more secure than anything possible with classical technology. The implications extend beyond practical applications to fundamental questions about the nature of information, computation, and intelligence itself. If quantum computers can solve certain problems exponentially faster than classical machines, what does this reveal about the computational structure of physical reality? If consciousness emerges from information processing in the brain, could quantum effects in neural networks contribute to aspects of intelligence that classical computers cannot replicate? These questions remain largely unanswered, but they illustrate how quantum technology development is driving deeper investigations into the relationship between mind, matter, and information. The study of quantum artificial intelligence explores whether quantum computers might exhibit forms of problem-solving and pattern recognition that transcend classical computational approaches. While no scientific evidence suggests that quantum computers could become conscious, the exploration of quantum information processing does offer new perspectives on the nature of intelligence and creativity. The development of quantum internet protocols promises to create global networks where information can be transmitted and processed according to quantum mechanical principles rather than classical ones. These quantum networks could enable forms of distributed computing and communication that are impossible with classical infrastructure. Imagine scientific collaborations where researchers can share quantum states directly rather than just classical descriptions of their experiments, or financial systems where transactions are secured by the fundamental laws of physics rather than mathematical algorithms. The social and economic implications of quantum technologies are already becoming apparent as governments and corporations invest billions of dollars in quantum research and development. Nations are racing to achieve quantum advantages in various technological domains, recognizing that progress in quantum technologies could provide decisive benefits in fields ranging from national security to economic competitiveness. The quantum technology revolution is reshaping not only scientific research, but also international relations and economic strategy. As you reflect on these developments, consider how they might influence your own life over the coming years. The smartphone in your pocket might eventually include quantum-enhanced processors that enable new forms of artificial intelligence and pattern recognition. The medical devices monitoring your health might exploit quantum sensors to detect biological changes too subtle for classical instruments to observe. The financial systems managing your savings might depend on quantum cryptography to protect against increasingly sophisticated cyber attacks. The integration of quantum technologies into daily life will likely proceed so gradually that most people won't notice the transition. Just as few people today think about the quantum mechanical principles underlying LED lighting or semiconductor electronics, future generations might take quantum computers and quantum communications for granted without appreciating the revolutionary physics that makes them possible. Yet understanding the quantum foundations of these technologies offers insights that extend far beyond their practical applications. The principles underlying quantum computing illuminate fundamental questions about the nature of information and computation. The mechanisms enabling quantum cryptography reveal deep connections between knowledge, security, and the structure of physical reality. The operation of quantum sensors demonstrates how the universe's most subtle correlations can be harnessed for human purposes. The philosophical implications of quantum technology development deserve careful consideration alongside their practical benefits. If quantum computers can perform calculations that are fundamentally impossible for classical machines, what does this reveal about the computational nature of reality itself? Some interpretations suggest, though this remains highly speculative, that the universe might operate analogously to a vast quantum computer, with physical processes representing information processing operations at cosmic scales. These ideas connect quantum technology to broader questions about the relationship between mathematics and physical reality. If quantum computers can solve mathematical problems that are intractable for classical machines, does this suggest that mathematical truth itself might exhibit features that align with quantum aspects. The exploration of quantum algorithms has revealed mathematical structures and relationships that were invisible from classical computational perspectives, hinting at deeper connections between quantum mechanics and pure mathematics. The development of quantum machine learning algorithms explores whether quantum information processing might enable forms of artificial intelligence that transcend classical limitations. While this research remains in early stages, preliminary results suggest that quantum computers may be particularly well suited for certain types of pattern recognition and optimization problems that are central to machine learning applications. If quantum artificial intelligence were shown to prove superior to classical approaches for certain cognitive tasks, this could provide insights into the computational principles underlying biological intelligence. While no scientific consensus exists about whether quantum effects play significant roles in human cognition, the exploration of quantum information processing does offer new frameworks for understanding how complex systems can exhibit intelligent behavior. As these quantum technologies continue to evolve, they will likely influence not only our practical capabilities, but also our conceptual frameworks for understanding consciousness, intelligence, and creativity. Growing up in a world where quantum effects are routinely harnessed for technological purposes might naturally lead to ways of thinking about possibility, correlation, and information that differ significantly from those shaped by purely classical technologies. The study of quantum entanglement in complex systems has revealed that these correlations can persist and even strengthen under certain conditions, challenging assumptions about where the quantum realm ends and the classical world begins. Recent experiments have demonstrated entanglement between increasingly large and diverse systems, from mechanical oscillators containing thousands of atoms to hybrid systems that couple light with matter across multiple physical domains. These advances suggest that the boundary between quantum and classical physics might be more flexible than previously assumed. While large, warm systems typically destroy quantum correlations through environmental interference, scientists are discovering conditions where entanglement can survive and even flourish in complex environments. This opens possibilities for quantum technologies that operate under less stringent conditions than current systems require. The implications extend to questions about whether quantum effects might play functional roles in biological systems under natural conditions. While most biological processes operate in environments too warm and chaotic to support the delicate correlations required for quantum entanglement, recent research has identified several biological phenomena that may exploit quantum effects for functional advantages. Photosynthesis in plants appears, based on current evidence, to use quantum coherence to achieve remarkable efficiency in energy transfer, with excitation energy exploring multiple pathways simultaneously through quantum superposition. Some migratory birds may exploit quantum entanglement in specialized proteins to detect magnetic fields with extraordinary sensitivity. Even certain enzymes are thought to use quantum tunneling to accelerate chemical reactions in ways that classical chemistry cannot fully account for. These discoveries suggest that evolution may have discovered ways to harness quantum effects for biological advantage, creating living systems that operate at the interface between quantum possibility and classical reality. While the evidence for quantum biology remains preliminary and controversial, these investigations illustrate how quantum principles could extend into domains previously considered purely classical. As you contemplate these possibilities, consider how they might reshape your understanding of the relationship between life and the fundamental laws of physics. If biological systems can maintain quantum effects under certain conditions, then the processes of life might involve quantum phenomena that classical biology cannot fully account for. This doesn't mean that life depends entirely on quantum mechanics, but it does suggest that quantum effects may contribute to the remarkable efficiency and adaptability of living systems. The exploration of quantum effects in biological systems has also led to investigations of whether contemplative practices might influence quantum processes in the brain or body, though this remains entirely speculative and unproven. Some researchers have studied whether meditation or other contemplative practices correlate with measurable changes in neural coherence or other biophysical parameters that could, in principle, reflect quantum mechanical processes. These investigations face enormous technical challenges, as detecting quantum effects in warm biological systems requires extraordinarily sensitive instruments and careful experimental controls. While some preliminary studies have suggested possible correlations between contemplative states and various biophysical measurements, the scientific consensus maintains that extraordinary claims require extraordinary evidence, and the evidence for quantum effects in contemplative practices remains far from conclusive. Nevertheless, the phenomenology of contemplative experience often includes descriptions that resonate at a metaphorical level with the principles underlying quantum entanglement. Practitioners frequently report states of awareness that transcend ordinary boundaries between self and environment, experiences of interconnectedness that echo the non-local correlations revealed by quantum physics. While these subjective experiences don't constitute scientific evidence for quantum effects in consciousness, they do suggest interesting parallels between contemplative insights and quantum discoveries. The contemplation of quantum entanglement naturally leads to reflections on the nature of connection itself, whether in human relationships, ecological systems, or cosmic structures. The discovery that reality operates according to principles of non-local correlation challenges classical assumptions about independence and separation. If particles can maintain correlations across arbitrary distances, if measurement of one system can instantaneously affect another regardless of the space between them, then our understanding of relationship itself may require fundamental revision. This quantum perspective on connection extends beyond physics to questions about consciousness, empathy, and care. While no scientific evidence suggests that emotional bonds create quantum entanglement between human beings, the parallels are striking enough to inspire thoughtful consideration. Both quantum correlations and emotional connections transcend ordinary boundaries, creating relationships that persist despite physical separation and influence the behavior of connected systems in ways that seem to defy simple explanation. These parallels remain firmly in the realm of metaphor and subjective experience rather than scientific fact, but they illustrate how quantum discoveries can enrich our understanding of human relationships even when they don't directly apply to them. The universe revealed by quantum mechanics is far more interconnected and mysterious than classical physics suggested, and this expanded view of reality naturally invites expanded ways of thinking about connection, compassion, and community. The future of quantum entanglement research promises discoveries that will likely surprise even the scientists working at the cutting edge of these investigations. Planned experiments will test entanglement across increasingly exotic scales and conditions, from laboratory systems to astronomical observations, from controlled environments to natural phenomena. Each new discovery has the potential to reveal additional layers of quantum interconnection that challenge our assumptions about the possible and the impossible. The space-based quantum experiments are beginning to test entanglement across truly cosmic distances, using satellites to create and maintain quantum correlations between ground stations separated by continents. These experiments will eventually extend to interplanetary scales, testing whether the quantum connections that seem so fundamental to reality operate consistently throughout the solar system and potentially beyond. The search for quantum effects in cosmological phenomena represents one of the most ambitious frontiers in quantum research. Some theoretical frameworks suggest that quantum entanglement may have played a crucial role in the early universe, shaping the distribution of matter and energy during cosmic inflation. If these ideas prove correct, the largest structures in the universe, from galaxy clusters to the cosmic web itself, could bear the imprint of quantum correlations established in the first moments after the Big Bang. The investigation of quantum gravity, the long-sought theory that will unite quantum mechanics with Einstein's general relativity, increasingly focuses on the role of entanglement in determining the structure of space-time. Recent theoretical work suggests that space and time themselves might emerge from patterns of quantum entanglement, rather than existing as fundamental features of reality. If this proves correct, it would represent a complete revolution in our understanding of the cosmos, revealing that even the stage upon which all physical events occur is itself a consequence of quantum correlation. These explorations venture into territory where physics encounters its own philosophical foundations, where empirical observation meets the deepest questions about the nature of existence. The study of quantum entanglement has already challenged classical assumptions about locality, realism, and the role of observation in determining reality. Future discoveries will likely force even more fundamental revisions to our understanding of space, time, matter, and consciousness. As you rest in contemplation of these profound mysteries, remember that you are not merely observing the universe from the outside, but experiencing it from within, as a conscious system shaped by physical law. The quantum correlations that enable entanglement are not separate from you, but constitute part of the foundation of your being, the substrate from which your thoughts, perceptions, and experiences arise. The story of quantum entanglement is far from over. Each experiment peels back another layer of mystery, revealing not answers, but deeper questions, more profound connections, more beautiful impossibilities woven into the fabric of existence itself. Tonight, we've journeyed together through a landscape where distance becomes meaningless, where particles maintain non-classical correlations across the cosmos, where the very act of observation shapes the nature of reality. We've seen how Einstein's discomforts with spooky action at a distance led to experiments that proved the universe operates according to principles stranger than any science fiction. We've explored how quantum entanglement enables technologies that transform abstract mysteries into practical tools for secure communication and revolutionary computation. We've contemplated how these quantum connections might extend into biological systems, into consciousness itself, into the very structure of space and time. Yet perhaps the most profound insight isn't about particles or experiments or technologies, it's about connection itself. In a universe where quantum correlations transcend all boundaries, where information flows through channels that exist outside ordinary space and time, the notion of true separation becomes questionable. You are not an isolated observer contemplating distant mysteries. You are woven into the quantum tapestry itself as a participant within physical reality, a conscious manifestation of the same correlations that link particles across cosmic distances. As you drift toward rest, carry this gentle understanding with you. The atoms that compose your thoughts were forged in ancient stars, scattered through space, and gathered here through physical processes that connect you to everything that has ever existed. In the quantum realm, distance truly disappears, in the sense that spatial separation does not limit statistical correlation, leaving only the eternal dance of correlation and consciousness as a poetic metaphor for the deep interconnectedness that binds all existence into a single, magnificent whole.